Hey, um, welcome to my stream. I'm just going to tweet out that we're live, and we'll go from there. Welcome back if you're tuning in again. Today we're going to make a clone of Tetris in Castle, and hopefully that will be fun. So the source code of what we're going to base this off of is something I made a little while ago, and you can find it on github.com/sheetcheever/quadrax-redux. Quadrax was like a Tetris clone I made when I was a kid, and Redux is just the second coming of it. The source code for this one, I actually made a jam band themed, which I won't bother with today. But this is kind of the code that this is all based off of. So, cool. What we're going to do is just go open Castle. Oops. Just hit the Windows key and type Castle. That's a good way to open it. And all right, here we go. We've got 2 people watching, so great. Welcome everyone. Say hello in the chat if you want. And so what I'm going to do here is I'm going to expand this window a bit, then create a new game. And then I'm just going to start with a blank project here. I'm going to call this Tetris tutorial. And we're going to create this project. And I'm going to open this. And then right click to open with VS Code right here. And I'm going to run this game in Castle. So I'm going to maximize this, minimize the chat for now, just so we can see more of the game. If I can do that. And give myself a little more vertical space here. Okay, cool. So we can see the beginning of our sort of hello world here. Here's our code. So we don't really need to change anything in our .castle file here, because we're just going to work with the default resolution in Castle for this, which is, let's look it up in the docs. So if you go to Castle Games and then documentation and then game dimensions and scaling, you can see that the default is 800 by 450. That's a pretty good size for what we're going to work with here. Like, we're not making some sort of little pixel thing that looks like an old arcade game or Pico 8 here. We're trying to just make something that looks like solid, but we don't have like super high res stuff going on here. So 800 by 450 is pretty good. We can also do like stuff at like 0.5 or 0.25 or whatever, and if the user's screen is bigger than 800 by 450, it'll be scaled appropriately. So the first thing that I'm going to do is just pull in some utility functions that I made earlier. We've done this a couple times before, but I'm just going to go into my Castle Utils repo. You're welcome to use this, by the way, it's open source, but you also don't have to. I don't think these are amazing pieces of code, but I think they're fine. And then we're going to go to the last commit, just so that we're getting a snapshot in time instead of risking having this update underneath our feet. And then we're going to pull in this log.lua and array.lua, which are mildly useful functions. All that log does is basically take an arbitrary number of arguments and print them out, and it'll print things like object tables or strings, things like that. So we'll just take the raw version of this, copy this, and then we'll load it in here at the top, and we'll say local log equals require this. Cool. And then we also want our array utilities here, because we're going to need those later. I don't need them for a little while, but since we're importing stuff and I know I'm going to use it, I'll pull it in right now. Copy the raw URL here and require this. Okay, so to start, we should probably think about like just drawing. Let's start with the board of the game board, kind of, and let's just like figure out how big we want it to be, and like kind of draw some basic grid just so we can get started. So we'll have a variable that we use to keep track of board state. It'll just be a table. We'll initialize it in load. So we'll say board equals this, and then we'll say let's use some constants for this so we can mess with it. So it's board width equals, I think 10 is normal, and then a lot of times people use 20 for the height of a Tetris screen, but then we'll add 4 to that so that a piece can kind of come in bit by bit, but we can keep track of the whole piece even if we're only showing part of it. So we'll add an extra 4 things for the next piece. So we'll say that's 24. And then we'll just say for x equals 1 to board width, do, and for y equals 1 to board height, do, and board table insert a equals this, a comma 0, and then so what we're doing here is for each column we're going to make a table that is basically like the entirety of it's just kind of a table of the things in that column. And so we're going to make 10 of these columns, and we're going to like insert them into this other table so that we get a 2-dimensional table. And then after that, what we'll be able to do is say sort of things like board like 3, 4, and that will be the third from the left and the fourth from the top. So this is how we've kind of initialized our board. We could also do something, actually, we could just use instead of doing this, we could do something where we say board equals array, that thing I just imported, create array, board width, board height, 0. This will make something that's a 2-dimensional array with the width as the first dimension, height as the second dimension, and then fill it all with zeros. And that would just let us skip doing all this manually. I think that should work. So let's see if that works, and then we'll log the board and see if it looks right. So now if I go here and reload this, I was tempted to get length of local number of dimensions, number of value. Okay, so I must be misusing that. Oh, I did use that wrong. This takes actually a table of dimensions and then a thing to fill it with. So add these brackets around here and then reload this. And then get rid of that variable total time elapsed. So I should bring that back for now, or actually just like get rid of this. just going to comment this out because we don't care about this stuff for now. Okay, so now we have a whole bunch of tables of zeros. So you can see we have 10 tables here that have 24 zeros each in them. Okay, so that worked. So we can delete this stuff here, and we can delete this manual code that was setting up the empty board. For now, we'll leave the log statement in just to prove that we're correct, but it's fine. And then we'll say we're just going to try to draw this now. So in love draw, we're just going to go, let's just use a function for this. So we'll say draw board, and we'll make this function draw board, and we'll say X, Y, S, so that we can like draw it in different places if we need to or whatever. And then we'll say, we don't need that yet. We don't even need these parameters yet. So we'll just say, okay, love graphics. We have to set the color so we can see what we draw. So we're going to make this like white. And then love.graphics, set line width 3. And then we'll draw a big border around the whole thing. Let's just say local x equals 200, local y equals 0, and local s equals 10. Size of each square in the board. So we're going to draw, this is just going to be a border around the entirety of the board, like kind of the well where the Tetris pieces fall into. So it's going to be a line. There's kind of two styles you can use when you're drawing a rectangle. So love.graphics rectangle. This is true of a lot of love graphics things where the first argument here is this mode thing. So you can see it takes something of type draw mode. If we look at that, it's going to tell us that there's either fill or line. So I can show you the difference between the two of them. We'll start with a line, but it'll basically be a line from x comma y to board width times s comma board height minus 4 times s, because we're going to leave 4 rows hidden. So let's see what this looks like. Alright, so we now have this like board that doesn't take up the whole screen, but is, takes up some of it. So we could make this bigger by making this S20. And now it takes up most of the board. Okay, or most of the sort of canvas area of the screen. Cool. It might even be fine if we made this line width even a little bit bigger. So we could say even like 6 or something here. Cool, that looks pretty good. And I'll show you what fill does here. I think you can guess, but if you look, bam, there, it's a filled rectangle. Okay, cool. But for now, we'll just use line. So that's kind of our border around the whole board. And then we're going to go through and we're just going to draw little squares at each place along the board. So we'll say for x prime equals 1 to board width, do. For y prime equals 1 to board height, do. actually, we'll just say, we'll start with 4 or even 5 because there's just going to be 4 hidden rows. And so we're going to draw, we'll set the color, love graphics, set color. We'll use, let's use something like gray here. That'll be easy to make. Gray is just like, instead of white is like 100% of each color, R, G, and B. And so gray is just like anything less than 100%. Using 50% is going to be, you know, kind of a medium gray. And then we'll use 1.0 for the opacity here. That's called alpha. Cool. So what we're going to do is now set the alignment to be a little bit less. We'll say, let's just say 1 or 2. Let's just say 2 so we can make sure we see it. And then we'll draw a rectangle at each place. So we're gonna have to do a little bit of math here to figure out where we should draw this rectangle. We'll use line for now, and then we'll kind of say x plus x prime times s minus 1, because we want the first one to be flush up against it, comma y plus y prime minus 5 times s to x plus x prime times s, comma y plus y prime minus 4 times s. Alright, hopefully that will draw a whole bunch of gray rectangles, and this will look right. It doesn't look right. So we got to figure out what I did wrong. Okay. So we should have had 10 things here, and yeah, okay, I know what I did wrong. If you look at the love.graphics.rectangle function, it takes x, y, and then width and height. I was giving it sort of an x2, x2, y2 parameters, and that's why I have this sort of weird looking thing here. So I'm going to delete this stuff, and then I'm just going to say s, because that's the size of each square. So now this should, okay, perfect. That looks approximately right. So now I can even just like scroll this down a little bit and it'll make my thing bigger. Cool. I can take out this log statement that sits on my board. Pretty sure that's right, so I'm not worried about it. So then the next thing I need to do is like draw stuff if there's anything at that board. So I'm going to draw just basically like based on what's at the entry in the board table, I'm going to draw something different there. So we'll say if board, like we'll say let our local c equals board x, y. And then if c equals 0, then we'll do this. Else if c, else we'll do something else. So this is empty square. Let's try setting up some stuff in our board where we just kind of stick some stuff in there. And we'll say board 10, 10 equals 1. So put one thing in there, and then say board Oh, we'll say 5, 5. That'll be easier to see. Board 6, 6 equals 2. Okay, so now at 5, 5 and 6, 6, we should have two different things. And so we'll say else if c equals 1, then we'll do something, else if c equals 2, then do something. We'll say we'll make this red, so it's RGBA, so red, that'll be 100%, 0%, 0%, 100% opacity. And then we'll just copy this, for now at least, and we'll say we'll fill instead of doing that. And then for blue, or for 2, we'll just do the same thing, but we'll do blue RGB, so the third thing is going to be 100%. And then hopefully we should see a blue square and a red square showing up here. No, it says attempt to index a nil value. Okay, so, oh, I used the wrong variable. I used x and y when I should have been using x prime and y prime. Okay, cool. So now I have a red square and a blue square. It's interesting that like I put the red and the blue square at 5, 5 and 6, 6, but here they are at the top of the screen. And just to remind you, the reason that's happening is because there's actually 4 hidden rows at the top of this thing that are actually part of the game board, but you don't see them. And the reason for that is when pieces fall down, we want them to sort of slide in, like not just like appear at the top in their entirety, but just kind of feel like they're falling from sort of infinitely high in the sky. So that's right, and looks pretty correct. So now we want to basically kind of draw, let's mix just like different colors for different pieces. So we'll say we'll make a table, and then we'll say 1 equals, we'll make 1 be red, just like an intense red. 2, we'll just make it be green, just kind of an intense green. And then 3, we'll make it kind of an intense blue. And then 4, we'll make it a yellow. We'll just combine red and green to make yellow. That's how it happens in computer graphics and light and stuff like that. And then 5, we'll combine red and blue to make purple. And then 6, we'll combine green and blue to make kind of a cyan. And then 7, we can just make it white. We'll just go 100% lit up across the board. So let's just think about what all the different Tetris pieces there are. We could figure this out ourselves, but we can also just like look it up. So there's sort of I, O, T, S, Z, J, and L. So there's 7 of them. So, okay, so we'll just say that these are, well, actually let's use, instead of using numbers, let's use like letters for this. I, O, T, S, Z, J, L. And then can't decide if I want to use numbers or letters for this. I'm going to use numbers. It feels easier to me. Okay, so let's see if this worked. And just make sure that our error parsing file. Okay, that's the kind of thing I was looking for. Where's the error parsing file? On main 16. Expected. I guess it just doesn't want me to give the numeric indices. So if I do this, this might work. Okay, that looks fine. So, I think what I can do here is just say else love.graphics.setColor colors C, and then I think there's some way to do this. Alright, I think there's a bunch of ways to do this, but one of them will just be to say unpack color C and then do this stuff. What unpack will do, it'll take a table and then put each of those kind of like in line as an argument to set color. So each one of these colors entries will be a table of 4 numbers, and this will unpack them and put them into the set color thing. So I should get the same result here pretty much, except I think that this blue thing will turn green. Yeah, okay, cool. And what happened there is that you saw that I was manually setting board 5.5 and 6.6 to 1 and 2. And so when we looked it up in the colors map, the first one was red all on, the second one had green all on, and so that's why that second dot is green. Okay, cool. So now the next thing we want to do is kind of so this will let us draw the whole board, and then we also maybe want to figure out how to draw pieces and like pick pieces and stuff like that. So what we're going to do there is we're going to want to have some kind of data structure that tells us what these pieces are shaped like. And so there's really 2 ways we can keep track of these pieces. One is we could use like an array, kind of like we have on the screen right now, where we keep track of like, is each one of these squares turned on or turned off? Or if we look at these tetrominoes, you can see that each of them have just like 4 squares turned on. And so another way we could keep track of everything is we could say, what are all the coordinates away from some place that are turned on in, the L piece and the J piece and the Z piece and the S piece or whatever. It'll be a little bit shorter to write out 4 pairs of coordinates than to write out an entire 4x4 grid, I think. So it'll be a little bit harder to read, but I think it'll be pretty reasonable in a lot of ways. So let's try it this way. So we can say, we'll make a bunch of pieces, and we'll have this one be named I, and that's going to be, we're going to have stuff at 2, 1, 2, 2, 2, 3, and 2, 4. And actually, we might as well just combine the color stuff in here as well. So we'll add another entry here, and we'll just take the entries from here, and we'll just keep track of this all. Well, we'll use an index actually. I take that back. So we're just only going to keep track of the pieces here. Okay. So then this is rod. So the next one that we're going to do is the square, or also known as O. So for that, this is going to be 2, 2, 2, 3, 3, 2, and 3, 3. We're picking these coordinates to try to center everything within a 4x4 grid, just so that when we rotate, it feels like we're rotating around something sensible. You can imagine if you're rotating a rod, if you put it flush left in a 4x4 grid, then when you rotate it, it would kind of be bordering the left side, then bordering the bottom side, then bordering the right side, then bordering the top. And that doesn't feel right for the way that you think of rotating it. Like you would think of it more as being like right in the middle and then kind of spinning around the center of its mass. So we're going to try to center all these pieces around there. Similarly, like if you think about the square, if you rotate the square, like nothing should happen. But if we put it on a 16 by 16 grid in the upper left, then it would kind of move from the upper left to the bottom right, or to the bottom left to the bottom right to the top right. And so that's why we want to center all these things, and we're using these sort of things in the 2s and 3s a lot. So this is called an O, or a square piece. Let's do a J next. So that kind of looks like this. So that's going to be 1, 2, 1, 3, 2, 3, and 3, 3, I think. That's a J piece. And then next we'll do an L piece, which will be 1, 2, 2, 2, 3, 2, and 1, 3. It's basically the same as a J piece, except just kind of a little bit inverted. Not inverted, just kind of flipped rather. And so then T piece is interesting and unique. So that's 1, 2, 2, 2, 3, 2, 2, 3. And then we've got an S piece. So that's kind of the one that goes like this. So that's going to be 1, 1, 1, 2, 2, 2, and 2, 3. And then we've got a Z piece, which is going to be 2, 1, 2, 2, 1, 2, 1, 3. Cool. All right. So let's just log this and make sure that we like are storing something sane in this, and that everything's like not crashing right now before we start trying to do anything interesting. Okay, that looks fine. Great. Wait, what just happened? Expected to close. Oh, I scrolled up is what happened. Okay, so that's fine. The next thing we want to do is kind of put a piece on the board and then draw it. I think what's going to make sense is for us to actually draw the board as all the things that have kind of already been placed and are kind of fixed in place, and then with the current piece that's falling, we know there'll only be one at a time, and we'll just kind of draw that separately afterwards. And when that lands, then we'll kind of copy over that data onto the permanent board. And I think that will be the easiest way to do this. So the way we're going to do the draw stuff is we're going to draw the board first, and then we're going to draw the piece second. And so then we just need to do draw piece. Okay, so for now, we need something that like keeps track of the current piece. So current piece, and for now in love.load we'll just say current piece equals pieces but we need a couple of pieces of information here. We need an x, and we'll just say that that starts at like 8, 8, an x and a y, and then we'll say piece equals pieces. Let's do an L piece, so that'd be 1, 2, 3, 4. Let me just add these indexes. 1, 2, 3, 4, 5, 6, 7. Just so I know. And then what others? Do I need to keep track of rotation? I think if I am gonna just keep the track of this way, I do need to keep track of rotation. So I will say rotation equals 0. Okay. So rotation will just be an index, and it'll be like kind of the number of times you rotate it right. So 0 will be like normal, and then 1 will be rotated 90 degrees to the right, 2 will be rotated 180 degrees, 3 will be rotated like 270 degrees, which is also the same as going left once. So we'll just keep track of the piece in the abstract, where it is on the board, and then its rotation. So that should work. Okay. So then we will say local x equals local CP equals current piece, and then local P equals CP.piece, and then we'll say S equals 20 here. We need to know where we're drawing this board, so let's move these. Out. Board y equals 0. This equals 20. I just need to reuse these variables, so I want to extract them out here instead of just typing them over and over again, because then it'll be harder to change. Okay, so board one. Okay, so now I'm gonna say for I equals 1 to 4, do local Can I do destructuring? I can't remember. I think what I can do, let me test. Well, let me save this and see if it works. Okay, so that's working fine. So I want to test is if I have a table like 4, 6, can I say local 4, 6 equals unpack 4, 6? Let's see. Log 4, 6. Okay. All right, we got a 4 and a 6 here from the log statement. So that did work. Okay, great. So, local x prime, y prime equals unpack p I. And so then we're going to draw a rectangle. Load.graphics, set color, colors. Ooh, wait. We're going to keep track. We're just going to use an index for the piece. Okay. Piece. We'll say we'll start with L. And then pieces. Okay, we just have a bunch of coordinates and colors. We have a bunch of colors. Okay. Unpack PI. Okay. And then we're just going to, for each of the 4 things in the tetromino, we're going to draw like a rectangle and fill it in at the appropriate coordinate. So we will say love.graphics.rectangle. Is that right? Is that what we called before? Yeah. We're going to say fill, because we're going to fill it in. And then we're going to say this is going to be x plus x prime minus 1 times s comma y plus y prime minus 5 times s comma s comma s. Okay, so hopefully that looks cool. And so now we should be drawing a piece. Oh, okay, that didn't work at all. Draw board, draw piece. Okay, so let's just make sure that this is getting called. Log, draw piece called. Because what I think should be happening is that this current piece that we initialize should be an L piece at 8, 8 with no rotation. We're not even doing rotation yet, but we should be drawing this. So let's just see if it's even being called. Okay, it's getting called all the time, so that's fine. So let's log SCPP X, Y and see what's going on with all those variables. Alright, so piece equals 4, rotation equals 0, x equals 8, y equals y. Is p something reasonable? P doesn't appear to be set. Okay, so something must be going wrong here. Okay, so now, what is this stuff? It's getting... $20, then a color, then a table, then 200, 0. Okay. Okay, that all looks right. But why are we not drawing stuff? Set color, set line width, rectangle fill. And well, first let's see if the color's wrong. We use kind of a medium gray here, just to see if we can, well, we'll use red just to see if we can get something to show up. And then line width 4, and then okay, those things look right. Let's see. X1 equals x plus x times s. X2 equals y. And let's see what happens there. Why is this not getting drawn? X1 is 4,000 for some reason, which is crazy. Oh, I think it's because, yeah, I need to not be adding that there. I need to be doing x plus that, and this is the danger of mixing sort of different units of stuff. So I had x was in pixels here, and then x prime is in an offset in the grid. So questionable coding to call them both x and x prime or whatever. But I figured that out by just like logging different things and noticing that these x and y location things were crazy. So hopefully if you run into something similar, that gives you some way to figure out what's going on. It's just like logging things until you see what's going on. The downside is that you generate a lot of logs really fast, because every time you draw you see them again. Okay, initializing again, loading it. Okay, I'm still not seeing anything being drawn, but it feels like we're making progress. Okay, so I'm a little confused right now, which is okay. That happens sometimes. My brain's a little fried from a long day. And I'm going to clear these logs because I think they're going back too far and I still managed to scroll to the top. And so, okay, so I can see now what's happening here is the y values are negative, so it's just too far up. And so, I think I just need to not subtract 5. I need to subtract 1, and that will be correct. All right, cool. Now I see a yellow piece appearing. Why is it? I thought I said it was at 8,8, so I'm not sure why it's showing up there. Oh, okay. Because I'm not adding in the x and y of the piece. So, okay. Current piece. All right, let's just do this calculation here and then we can log it if we have to. So what I'm doing here is just doing the computation here so I can log it, and then using that value, the rectangle here. I'm still using this questionable thing where in some cases the x means like a coordinate, and in some cases it means like an index, and that's probably not good to mix those. But we'll just deal with it for now. Hopefully this will show up in the right position where I want it to. All right, it did. So you can see one thing that's interesting here is that this piece is like flying off the end. And so what we're gonna have to do is not just check to see if the piece is somewhere between 1 and 10 on the x coordinate, we're actually gonna have to check to make sure that like each part of it doesn't go over the edge when a piece is coming down. And so that's gonna be interesting. Okay, Cool, but we can at least draw a piece now and stuff like that. So let's make a next piece function that just kind of sets up a random piece in the right place. And it'll set current piece values, and it'll say y equals 1, x equals 5. Well, we'll say 4, because these things are 4 wide, so 4, 5, 6, and 7 leaves 8, 9, and 10 on one side, and 1, 2, and 3 on the other side. So that feels about right. Although, yeah, I guess that's right. And then the piece should be a random number between 1 and 7. And we're going to say is math.random uh, 7, and then rotation equals 0. And what else do we need? That's it. Okay, cool. So now we'll just say current piece equals next piece. So if I did that right, we should be putting a piece at the top of the screen. If everything worked out. Huh. I wonder what's going on here. Maybe I have too many I don't know what's going on. Oh, that's working again. Okay. Unable to index up value, current piece, and no value. Where is that error coming in? 64. Okay, current piece. Do we not? Oh. We don't have any return value here, so we'll just say next piece, and we'll use the side effect of this function instead of trying to capture the return value. Okay, so clear, restart. Okay, so that's fine. And then if I give a y value of like 7, now this should show up, the piece should show up on the screen. All right, cool. Now let's just try capturing key presses, and then we'll use that to kind of like just cycle through different pieces. So, okay. Here we'll just say function key press, I think is what we were looking for. And I think that's right. Yeah, so we'll just Google that. And so this gives us 3 arguments: key, scan code, and then is repeat. And so for now, we'll just say we don't care what key it is. Anything, we'll just make a next piece. It doesn't matter if it's a repeat, doesn't matter what key it is, doesn't matter what the scan code is. So here we go. Cool. So now each time I hit a key, we get a different piece stuck on the board here. So I can see when I have the rod, there's 1, 2, 3, 4, 5 things open on one side and 4 on the other. When I have this, I have 1, 2, 3, 4, and 1, 2, 3, 4. When I have this, I have 1, 2, 3, 4, and 1, 2, 3. I have 1, 2, 3, 4, 5, and 3. I should move this over actually 1 to make it totally centered, based on the way I've done this. So when I do next piece, doing current piece, I should say x equals 3. And now if I reload this, now all these pieces should just be a bit more centered as they enter the board. so that squares are centered. This block is a little off center. Well, it's hard to say. I go back to 4. But either way could probably work. Okay, so we're going to take out this log statement because I think it's making everything just like have degraded performance, and we don't need to do it anymore because we sort of have some confidence in our ability to draw pieces. So if I reload now and clear these logs, it should be a little bit less yeah, okay, so this just works pretty smoothly now. Okay, that's pretty nice. And so now what we're going to do is we're going to say if the key is, we're going to not do a next piece every time, but we'll say if the key equals left, then we're going to do something. If the key equals right, then we're going to do something. And we're going to say current piece X equals current piece X, and CPY equals current piece Y, and current piece rotation equals current piece rotation. So we're going to keep track of the X and the Y and the rotation of a piece. So if it moves to a bad state, we can still, we can just undo that. So if we want to move the key left, then we'll say current piece.x equals current piece.x minus 1. And if we were going to move right, we're going to say equals current piece.x plus 1. Okay, so we're not going to do the canceling yet, but we're setting up to do it in a minute. So right now, if we do this, we should get one random piece at the beginning. If we push left, it should move to the left, and if we push right, it'll move to the right. Okay, so the first thing we can see now is that it's flying off the edge of the board. And so what we want to do is make sure that it can't do that. So what we're going to do is we're going to go through each of the 4 pieces of the thing, and we're going to figure out where they are relative to the thing, relative to our sort of X and Y coordinate that we're keeping track of in current piece, and then see if there's anything wrong with putting a block there. And so we're going to say for I equals 1 to 4, do local offset X equals pieces, okay, local piece equals pieces, current piece equals P I 1, local Y equals P I 2. So we could probably say X equals unpack PI. Okay. So, okay. So now we'll log OX and OY and just see what happens and make sure these values seem reasonable. Okay, they seem pretty reasonable to me. So then now if we're going to factor in rotation, that's another beast. So let's start doing the rotation thing first, actually. So we'll say current piece dot rotation equals current piece dot rotation plus 1, and then let's do modulo. How do you do modulo? I think you just use %. So if we can do modulo 4, that means if we get to 4, we'll just go back to 0. The reason for doing that is that we don't want this number to get sort of insanely huge, because it might get more complicated to compute something, or it's just easier to deal with smaller numbers and just know that it's always going to be either 0, 1, 2, or 3. And then what we wanted to actually do is get the positions of all the coordinates based on a piece and thing. So let's actually break that into another function. And so we'll say that it's always of current piece. It'll just be easier that way. And so we'll say offsets equals empty table, and then we will say for I equals 1 to 4 do, and then we'll say local p equals pieces current piece, and then oxoy equals unpack pi. But then if we're going to do any rotations, we'll need to do that. So the way that we do rotation is just to do a little bit of arithmetic. And so the way that we can do that arithmetic is basically each time we rotate right, we'll say that like x and y kind of switch, but then x turns into y, and x turns into y, and y turns into 5 minus x, I think. So for j equals 1 to current piece dot rotation do ox equals I wonder if this is going to work. Can you do a swap in Lua by doing this? Okay, you can do swapping. Okay, so this means this will work. Cool. I don't want to, like, because the new OX and the new OY depend on the old OX and the old OY, it's convenient that I can use a comma here and just do this all in one line instead of creating a bunch of temporary variables. So OX is going to be OY, and OY is going to be 5 minus OX. Okay. And so then we'll rotate that. And so this is one reason why we don't want the rotation to get really, really large, because if you got that up to be 1,000, we'd just be doing a lot of extra arithmetic. It doesn't really matter for something this simple, but like, why not just try to get it right? And so, okay, so then that means that if I do this, then each time I push the up key, this should rotate a little bit. Oh great, I got a square, so we'll never be able to tell if that's actually happening. Okay. So, okay, we're not using this, so, okay. Let me go back into the draw piece function and use the get offsets. Local offsets equals get offsets. Okay. Local x, y equals unpack offsets I. Okay. Cool. So now, in theory, this should draw offsets of no value in 70. Offsets get, oh, I'm not returning anything from get offsets, am I? So I go through these things, and I need to do each time table dot insert offsets comma ox comma oy. What table dot insert does is it just sticks an element into a position. Oh, it looks like the table is the first argument, so I should be doing this. Oh, no, I did that right. Okay. Oh, I still need to return offsets here. Cool. Okay. So now I can rotate this and move it left and right. Awesome. And then I'm also gonna let us say else if key equals down, then current piece dot y equals current piece dot y plus 1. This will let us move the piece down with that. Cool. So now I can rotate it and move it left and right and move it down. Cool. The other thing that's cool about this is now I can say get offsets, and I can go through these and check to see if there's anything wrong with any of these coordinates. So the first thing I'll check is just like local x equals current piece dot x plus ox, local y equals, I'll just do it all in one line, local x comma y equals current piece dot x plus ox comma current piece dot y plus oy. So now I can say if x is less than 1, then let's say undo equals false, then undo equals true. Else if x is greater than 10, then undo equals true. Else if y is less than 1, then undo equals true. Else if y is greater than, I should be saying board width and board height here, undo equals true. Okay, so we'll just check for now for these things, and we'll say if undo, then log invalid. So we'll just be able to tell if we've moved the piece into somewhere invalid. Okay. Oop, expected then near undo. Okay. So clear these logs, and so now if I go to the left, then when I come off here, oh great. When I'm off, you can see that different pieces are sort of saying, oh, these are invalid. That's awesome. So instead of just saying invalid here, what I'm going to do is say current piece.x equals this old cpx, and current piece.y equals the old cpy, and current piece.rotation equals CPR. So yeah. So cool. So now I can check all the ways I can move stuff, and now I'm not actually allowed to do these different things. And so I'm going to add another thing that lets us switch pieces. Also, key equals space, then next piece, return. I don't want to do all this checking for invalid stuff if I'm doing a new piece, actually. So I can move these pieces around, rotate them, get them up against the edge, and move them down if I want, and then space will give me a new piece. All right, beautiful. The next thing we want to do is just check to see, in addition to just seeing if it's going off the edges, just to check to see if there's anything in the way in any of these spots. So else if board x, y doesn't equal 0, then undo equals true. So that way we won't let you collide on top of different things. So let's add some more stuff to the board. So we'll say board 8, 10 equals 3, board 8, 9 equals 3, board 8, 1 equals 3, board 8, 2 equals 3. So now we're putting some things in the way here that, yeah, so now it won't let me move through these blocks, which is kind of nice. Huh, I'm surprised that only some of these things, 1, 2, 3, 4, 5, 6, 7, 8. Oh, rows 1 and 2 don't mean anything. Okay. So these are actually kind of y, comma, x. But we'll just keep going with this for now. Cool. And so then now we want to detect if the thing is at the bottom and needs to kind of stop moving. Well, we can also just make it move down with love.update. So maybe the best way to do that is just to kind of say, actually I'm going to pause for now that we have this thing working, and I'm going to continue this in a further stream because this has gone on for like an hour and 20 minutes. So I think that's kind of longer than a normal stream. So I'll come back to this in a stream in a couple of days. Thanks for watching and have a great day.